So there we go. So this session is again recorded, but chat is not included in the recording. So today's topic is Arduino stuff, or this afternoon, as usual, Arduino. And now basically it's about how to connect the real world, meaning analog world, with a microcontroller. So we are getting closer to the connecting things. First, we connect things, the microcontroller to sensors and such kind of things. And this is the good start for that one. From the last session, last week, we had the interrupts, counters count, and timers measures time. So now we basically build on this one. And to start the connection with real world, I start with the digital to analog conversion for a good reason, but the reason will be given later. So what is digital to analog conversion, or DAC, DAC? That actually creates an analog voltage on a digital device, and it's basically common applications like audio generation. They are using D to A converter, and when you are talking about those devices what you have on your computer, there's those sound cards and mobile devices have at least 2 channels. So that's stereo, at least. The 2 channels with a separate DACs with quite high resolution. 16-bit is not quite high yet, but it's high enough for CD quality audio. 24 bits is a lot. And sample rates for how fast they are actually sampling the data output is between 48 to 192 kilohertz in general. Some industry standard values there. The resolution there, the 16 to 12-bit resolution, what does it actually mean? Well, that's actually the means how small voltage changes the DAC can generate. For example, if you have a good quality audio output, digital audio output, analog output from a digital device, you have 24-bit DAC, let's say. And if the reference voltage here is the highest voltage you can get when you have all this data is all ones. So the highest digital value corresponds to 5 volts. Then that 24-bit DAC actually produces 0.3 microvolt steps. 0.3 microvolts is very hard to even measure with the professional equipment. It actually noise levels are around that level. Actually, noise levels are usually higher than that level signal. So that DAC output is basically the resolution there is very high. But on the other hand, then there are these lower resolution DACs. And so on. The sample rate means how often the output changes. So on sound card, there's a timer which actually gives the data. So basically the data is on table and there's a timer that goes once in a sampling time and reads that data and sends it to the DAC. So basically it's not continuous signal, but it's a discrete time signal. So, and if you think of human hearing, we can hear up to say 20 kilohertz physical signals. In order to hear those, or um, in order to produce that signal, you need to sample at least on the top signal and the bottom signal. So you need 2 samples for each the wave length, at least 2 samples, which means that okay, sampling rate must be at least 40 kilohertz. That's why the sound cards have the sample rate 48 to 192 kilohertz. Other applications, well, video signal generation, motor control, calibration, various things. Radio, there's direct digital radio, so even producing radio signals, RF signals from a specific RF controllers, and so on. So software-based radio transmitter, lots of different applications. So that's the wraps up more or less their DAC and some history. Okay, about 30 years ago when I was young, about your age, a Covox Inc. from USA launched an audio interface for computers, which was based on Centronics port, which was the parallel printer port. Parallel printer port. Or actually, parallel port of PC, the original PC, which could be also connected to the printer, let's put it this way. And there, it was very simple device, no active components, only resistors. And the schematic is there on your right. It's quite genius actually. These are the higher bits and these are the lower bits, and basically when you set high state here, you get some of that current flowing through the output, considering there's some sort of load resistor here, smaller load resistor. But anyways, some of that current is actually produced, and then basically you have the similar thing, but for the next. But there is 2 resistors here, and the resistors are actually they are set so that you get half of the current from this bit, and again half of this current on the next one. So basically this one sets the current output of that device based on which of those pins are ones and which are zeros. So it makes the digital to analog conversion. Okay, that's history. If you're more interested about the history and what happened to Covox, then you might be checking the those Wikipedia links there. But it's historic equipment and yeah, D to A converter. Audio levels are all over the place. That's interesting. Let me turn off and on my audio again if it works better. Sometimes it helps. Just a moment. I hope that this helps. That was strange. It hasn't happened before. Okay, analog to digital conversion. Actually, what I'm looking at my audio monitor for this recording, that seems to be working just fine. So it might be the Zoom that is mixing this signal somehow, messing up my good signal. All right, so analog to digital conversion. Another the digital converters. So analog to digital, just like the name, it measures the analog analog voltage levels against a known reference voltage. So basically, it's a voltmeter. It's a voltmeter, nothing else than a voltmeter. There are different types of AD converters, just like any electronic circuits. They are designed for purpose. So a general purpose A to D converter does not exist. They're always designed for some specific purpose, or if it's designed for general purpose, then it's usually very expensive. So there are some variables like converter resolution in bits, how many bits it has, time to perform a conversion, so basically the maximum sampling time, then the frequency responses, etc. There are the current output, their voltage output, or current input, their voltage input, and they vary from say 32-bit A to D converters that can measure, say, nanovolt level, but the conversion time can be in order of seconds, up to video frequency or radio frequency converters with 1 gigasamples per second, 1 gigasamples per second, but only say 8 bits or so. But okay, there are variety of things. When you're talking about the controllers, what kind of the A to D converters they have inside, built in inside? They are usually good for simple tasks like measuring a line voltage, but not really good at, say, any high-end conversion. For example, getting audio signals in. For that one, there are separate A to D converter available. But anyways, on the microcontroller ADC, the sensors, they have lots of different the analog sensors available, and how to connect an analog sensor into a digital network is you have A to D converter on microcontroller, and then it reads the data, makes it so that it can be sent forwards, and then it's, for example, it can send it to some cloud service or something like that. So that's IoT. Okay. Other typical applications: recording audio, video, and other signals, radio signal reception, so smartphones, digital TVs, the software defined radio, that kind of stuff. So practically tendency is to try to eliminate as much as analog electronics as possible. Some analog electronics are still needed, so you need to take care of some of the signal processing before you can convert it, for example. And on the other end, if you are running a digital to analog converter, you may need to have a post-processing filters, analog post-processing filters afterwards, that kind of things. So analog electronics is still needed, although everything is going digital as it should be. Arduino, it has 10-bit A2D converter with 5 volts reference. So practically it means that the it's about 5 millivolt step size in that conversion. So the maximum sample rate is around 10 kilosamples per second, assuming that the MCU doesn't do anything else. Part of that A2D converter is based on software. So it's not a separate unit that does everything. All the conversion by itself, and then you just go and read the value. It's basically a different type of A2D converter that is ran by software. So there's a single A2D converter, but there are 6 pins you can use as analog input. And you choose that signal by basically setting a multiplexer. So practically it means that when you call a analog read, then it read from a pin, then it switches the multiplexer on to that channel, and then it measures the voltage. And then you can move to the next pin. You cannot measure multiple pins at the exact same time. That's one of the limitations by using it multiplexed inputs. Okay, but anyways, it works. So the conversion between voltage and the ADC count is simple. It's ADC count multiplied by the reference voltage, which was 5 volts, divided by 2 to the power of bits. Okay, so 0 means that the input value is 0 volts or less. Okay, it can be a little bit negative, but it shows up as 0 count. Then the maximum value of 10,023 means that the input signal was either 5 volts or a little bit above that one. When you have a sensor, a separate sensor, it may actually give signals that are smaller than 0 or higher than that 5 volts. And it actually even can break the chip if that happens. But anyways, the Arduino A2D converter. It's so-called Successive Approximation A2D converter, and it's quite genius actually. I have some of the pictures later on, but anyways, the successive approximation is based on guessing the value by, well, if you are familiar with Newton's the half-point method, then this is the digital. Digitally, it's the same method. So we have that 10-bit D to A converter, which has a reference voltage for it, and conversion logic here, which is holding the our guess. Then there's sample and hold and comparator. Okay, sample and hold, meaning that when you have the, when you have the input on one of those pins, input multiplexer, then it takes the signal to a comparator, and the only function for that comparator is, first of all, it holds the value, input value steady during the conversion. That's quite crucial for this A to D converter. But then it also compares if that DAC value is lower than or higher than the input. And the output is thus going into the conversion logic. Okay, so that's the logic inside of the Arduino, the A to D converter stuff. We'll go to the how does it actually do the thing later. But okay, couple of notices. There's a reference that can be used for D to A converter, so that's the reference for the value for this A to D conversion use. Reference is 5 volts. Okay, on the input mux, this depends on which kind of processor you have, but there's also a way to calibrate. You can actually turn on the band gap reference, which is very precision, the band gap type of voltage reference that you can measure using that A to D converter. And then you have exactly, you know that, okay, at that point I have exactly, say, 1.1 volt or something like that. Another point, you can also calibrate A to D converter by grounding the signal, which means, okay, this should be 0. So now you have 2 points and linear the behavior of that A to D converter. So you should actually be able to also calibrate things. Nice. There's also notice about the power pin. If there is, they separate power pin for digital and analog part of a processor, any processor. You always use them also as separate. Digital power line usually have lots of noise due to the switching of these transistors inside of logic circuits. So it's a good practice to have a dedicated power line for the dedicated power line for analog part of any mixed signal circuit. Okay. How the successive approximation ADC volt converter actually works. There are some simulations. So basically, it starts guessing the value. In here, for example, we have the 5 volts reference, and input is 3 volts, and this actually compares the input to our guess. So first you go and turn on the highest bit, most significant bit, which is equal to half of the reference. So that's 2.5 volts. Okay, we are lower than our input. Next bit, we try first that if it's the next bit is 1. Okay, that's a 1.25 volts more, so we are at 3.75 volts there, which is higher. The comparator say, okay, now you guessed wrong, go back. And then it basically goes back and tries the next bit. By going this way, after 10 comparison cycles, you have the final A to D conversion result. I think this was quite educational, this approximation. The here animation. Okay, so when we have 0 volts, now we have 0.5 volts. You see the bits clicking, and okay, 1 volt when it goes lower, and okay, then the values. So results, for example, that, there we go. So practically when the voltage changes, it always the guesses, starts guessing by setting the bits, and okay, there. So it's going by halving the previous step, either higher or upper. And after n guesses, you are exactly at the, well, close enough for the real A to D conversion value. Good. That's actually a pretty good way of doing A to D conversion. Let's talk a little bit about sampling. A to D, the process of measuring voltage using A to D is called sampling, but actually it's not, it's an older than A to D converter. There's a Shannon's theorem on from 1949. If a function xt contains no frequencies higher than b counts per second, it is completely determined by giving it ordinates at a series of points spaced 1 or 2b seconds apart. Okay, what does it mean? The sampling rate needs to be at least 2 times the highest frequency component in the input signal. If it's not, then you really don't see what is happening on your signal. And actually, before the sampling, you should either have the high enough sampling rate or filter out these too high frequency components. If you are sampling with high frequency components, then you are bound to have a big messy data. No doubt about it. It happens always. Okay, real life example. If you measure outdoor temperature by every 20 hours, what you can make of the resulting graph? So 20 hours, a little bit less than one full day. So basically, you cannot really say anything about the temperatures, since the day and night temperatures are kind of mixed there. Or measuring once a month or once a week, taking a look at a Monday temperature at 7 a.m., for example, it doesn't say anything about the rest of the week. So you need to have enough of sampling points to get sense, make sense out of this data. And that's what's called aliasing. If we have a too slow sampling rate compared to the signal frequency, this kind of thing happen. So here we have the analog signal is the blue one, and then the red ones are sampled at quite low sampling rate. And as you can see, actually, well, it still looks like a decent signal. It's sinusoid, just like the analog, but it's totally messed up. It's not the same signal anymore. So basically, you don't know anything what you are measuring. So basically, to avoid sampling, the sampling rate should be at least 2 times the highest frequency in the signal. So for audio signals from 20 to 20 kilohertz range signal, you need to have at least 40 kilohertz sampling rate. That's why we have this 44.1 kilohertz standard sampling rate, or 48 kilohertz is another one, or 192 kilohertz is another one. So that's why we have different sampling rates and, well, high enough sampling rates. Real life example. Spokane, Washington, United States. Why Spokane? Well, because the data was easily available. They are fond of open. Actually, the American, this National Organization of Atmospheric and Oceanic Research, and also which correspond to the Meteorological Institute, they are fond of open data. They have always been fond of open data. For example, this weather satellite data, you can get it. Actually, you can get it free. Of course, it pays some to get the satellite dish and the receiver, but it's open. It is open. When you sample temperature every 24 hours, so what you can say about this one? What temperature is it? Is it daytime temperature? Is it the temperature at night? So every single day, the same time. Was it on night, day, evening, afternoon? So this data is bound to have a bias. Okay, bias or not bias. Let's see another way. Exactly the same data. Temperature is sampled by every 48 hours. So a little bit faster than every other day compared to that one. This may have a bias. It's 24-hour sampling time. I would put, say, faster sampling time. But actually, when you compare this one, this actually shows the annual change. So January around 0, then it for the summer comes, and then it actually may go above 30 degrees, and then again it goes down to 0. So practically it looks like in Helsinki, except in Helsinki it might get even colder, but about the same. Okay, same data. Temperature sample is 47 hours. See my point. There are anomalies that really cannot be explained here. How come you barely can see this the annual variation? Summer and winter, well, there's a small change, but there's more, say, weekly variation of data or temperature. So could it be that during this month, about June, it would be 10 degrees, then about 20 degrees for July, and then August 10 degrees, and then again 25 degrees. This is coming from the aliasing. So you sampled day and night temperatures and mixed those. Some of those are daytime. I would say these are daytime temperatures, and these are nighttime temperatures. Okay, so sampling matters. It needs to be fast enough. Okay, still the same data, but this gives you already maybe a little bit too much information. This is sampled by every 4 hours, which shows the daily variation. Although, of course, okay, I agree. The graph is a little bit messy, but actually it shows how much, for example, in here in January, the temperature has been varying between, say, -8 to +8 degrees. Average is about 0. Then it has dropped for a few days sub-zeros, and then here rises above 0 level again. And actually, this is when the thermal spring is, when the average temperature reaches 0 degrees. Thermal summer in, I think it was thermal summer starts when the average temperature is around, was it 15 degrees? That kind of thing. So you can see things. Yeah. So by showing all the data, it shows minimum, maximum. And next we go back to the low pass filtering. This is digital data. We cannot RC low pass filter it. We must do it actually digitally. The digital signal processing is an art of designing digital filters. That will be, I think it's on the 3rd year, fall semester, 2nd period or something like that. And Jarkko Vuori is teaching it for you. So basically, you need to, quite often in digital signals, you need to do some low pass filtering. If you have low pass filter before A to D conversion, then you can prevent aliasing effect on the data. But you can also reduce the amount of the noise before sampling. Remember the previous picture, one of those where the sampling rate is every 47 hours. We could do now the calculations again and not just pick the values. So practically the higher picture was the one where you just pick the value. So you sample from an existing data. So there was probably that 4-hour sampled data, and then you just pick values at, no, actually, that must be so that it was 1 hour data to resample the 47-hour sampling rate or sampling time. When you just pick those sample, you still have on the original data, you have these higher spectral components. The lower graph has a digital low pass filter before sampling. The filter actually removes it averages the data. So you cannot see anymore the daily variation, since this filtering has smoothed them out. But on the other hand, you don't have these artifacts that shows, okay, 1 month you have 10 degrees, another 25, 10, 25, which is total garbage. This lower picture shows that, okay, when you do this sampling correctly, meaning that before the sampling you will get rid of this noisy part, high frequency noise on the data, meaning you will filter the data before sampling, then you are on safe. Then your data is meaning something. Now it shows actually mean temperature variations during 1 year. Okay, back to Arduino. So the previous was in general about sampling. Remove the sample fast enough or remove any high speed components, high frequency components before sampling. Sampling is done when you are doing A to D conversion, or it also sampling is done also when you just pick values from data. If you're not using every single data point, but you go and pick just every 10th or so, that's also sampling. And filtering should be used. Okay, in Arduino everything is easy. It has its counterpart, but it's actually that Arduino you cannot really do just everything. It's simplified, simple system. But anyways, the sampling is made easy. It cannot get any easier than that. You just read the analog the pin value, and it returns the ADC count as integer. And in Arduino Uno, there are 6 ports from A0 to A5 that you can use. And the corresponding voltage follows this formula here. So there's a voltage equals ADC count times the reference voltage divided by 2 to the bits. So actually down there, this 2 to the bits is 10 bits. It's 2 to the power 10. Okay, easy to measure what is the corresponding voltage. And how to use it. There's again the reference. Let's take a look at it. Analog read. There. Yep. So one single bit actually means about 4.9 millivolt, 4.9 millivolts per step. Yeah. So analog reference. The resolution can be changed, but I wouldn't do it. So or not on this board. Just use that whatever there is analog reference. Okay, demonstration. Demo time. Excellent. Let's see what this demo is all about. Gallery of things. Copy and tinker to see what kind of tools there are for Arduino. Okay, it seems that there is a variable resistor. That one here connected so that it actually you can select any voltage value between 5 volts, which is on one terminal, and then 0 volts ground on the other terminal. By turning this knob, actually it gives different voltages to A1, and I would guess there's also some code. That's great. So there is a analog pin A1. That's the just a variable, and then there's funny setup command. Only serial begin. So serial pot is initialized for 9600 bits per second. And then we just read the value, and then serial print that one, delay a little while when I turn that simulation on. I can open the serial monitor, and okay, it's 655 is coming, and I can change that count value according to, yeah, between 0 and 1024. And what is actually even nicer, you can also take a look at the graph. So you can also see signals, say time dependent signals there. So that kind of nice small simulation. Feel to try yourself. Good. So, any questions at this point? Now we have a 5-minute break otherwise.